In the following video, we're going to explore 5 exciting new battery technologies that could change everything. Metal air batteries have been around for a while. You might find a little zinc air button cell in a hearing aid, for example, but scaled up aluminum and lithium air chemistries are also promising for the automotive and aerospace industries. The potential for lightweight batteries with high energy storage makes this battery technology promising. Lithium air batteries could have a maximum theoretical specific energy of 3,460 watt-hours per kilogram, almost 10 times more than lithium-ion. Realistic battery packs would probably be closer to 1,000 watt-hours per kilogram initially, but this is still 3 to 5 times higher than lithium-ion batteries can achieve. As usual, this technology is not without its drawbacks. Current electrodes of lithium air batteries tend to clog with lithium salts after only a few tens of cycles. Most researchers are using porous forms of carbon to transmit air to the liquid electrolytes. Feeding pure oxygen to the batteries is one solution, but it's a potential safety hazard in the automotive environment. Researchers at the University of Illinois found that they could prevent this clogging by using molybdenum disulfide nanoflakes to catalyze the formation of a thin coating of lithium peroxide on the electrodes. Their test battery ran for 700 cycles, compared to just 11 cycles of an equivalent with an uncoated electrode. While this isn't enough lifetime for a car, it's a promising hint of things to come. More on nanotechnology later. NASA researchers have also been investigating lithium air batteries for use in aircraft. They believe that once their research cell is optimized, they should be looking at around 800 to 900 watt-hours per kilogram, powerful enough to reach the high power requirements of takeoff. But they too are struggling with low battery life. For them, the solutions will boil down to improvements in the electrolyte. In an interview with Chemical and Engineering News, researchers commented, "From an organic chemistry perspective, the challenge of lithium oxygen is that you're basically asking an electrolyte to face many of the harshest reactive oxygen species possible." They are now investigating molten salt electrolytes, but hope to carry over the research into solid-state alternatives in the future to improve battery lifetime and cyclability. This technology still has a long way to go before you take your next business trip in an electric passenger jet, but the promise of such high specific energy will hold researchers' interest for the foreseeable future, driven on by the promising advances made in recent years. Nanotechnology has been a buzzword for several decades, but is now finding applications in everything from nanoelectronics to biomedical engineering, and body armor to extra slippery clothing irons. Nanomaterials make use of particles and structures 1 to 100 nanometers in size, essentially one size up from the molecular scale. The magic is that they behave in unusual ways because this small size bridges the gap between that which operates under the rules of quantum physics and those of our familiar macro world. As we've seen, one of the challenges in battery design is the physical expansion of lithium electrodes as they charge. Researchers at Purdue University made use of antimony nanochain electrodes last year to enable this material to replace graphite or carbon metal composite electrodes. By structuring the metalloid element in this nanochain net shape, extreme expansion can be accommodated within the electrode, since it leaves a web of empty pores. The battery appears to charge rapidly and showed no deterioration over the 100 charge cycles tested. Carbon nanostructures also show great promise. Graphene is one of the most exciting of these. Graphene is made up of a single atomic thickness sheet of graphite, and it turns out that this material has very interesting electrical properties, being a very thin semiconductor with high carrier mobility, meaning that electrons are transmitted along it rapidly in the presence of an electric field, as inside a battery. It is also thermally conductive and has exceptional mechanical strength, about 200 times stronger than steel. Grabat, a Spanish nanotechnology company, are pursuing graphene polymer cathodes with metallic lithium anodes, a highly potent combination if their electrolyte can adequately protect the metallic anode and prevent dendrite growth. This battery promises to be lighter and more robust than current technology while charging and discharging faster and with greater energy capacity. Samsung have patented a technology they call graphene balls. These are silicon oxide nanoparticles which are coated with graphene sheets that resemble popcorn. These are used as the cathode as well as being applied in a protective layer on the anode. The researchers found increases in the volumetric density of a full cell of 27.6% compared to an uncoated equivalent, and the experimental cell retains almost 80% capacity after 500 cycles. Additionally, charging is accelerated and temperature control is improved. Nanograph, meanwhile, are using graphene sheets to produce carbon-silicon batteries to increase stored energy by 30%. Amprius goes one stage further with their anodes of 100% silicon nanowire. The maker claims that they can achieve 500 watt-hours per kilogram, which is in the range suitable for enabling electric aircraft. Airbus Space and Defense announced a partnership with the company last October. The silicon nanowires are attached to a thin foil by vapor deposition in a continuous roll-to-roll production process, helping keep manufacturing costs down. The clever part is that these finger-like projections are porous on a micro and macro scale, allowing them to swell freely without significant expansion of the whole electrode, just as trees swell with leaves in spring, but the forest remains the same size. Some internet sleuths concluded that the company was recently acquired by Tesla because Amprius recently moved their headquarters right next to a Tesla facility. But Elon Musk debunked these claims on Twitter, saying, "But actually nothing, was surprised to hear they're across the road. Adding silicon to carbon anode makes sense. We already do. Question is just what ratio of silicon to carbon and what shape. Silicon expands like crazy during discharge and comes apart, so cycle life is usually bad." Nanomaterial research is promising. The University of California, Irvine have even produced electrodes good for 200,000 cycles using gold nanowires and manganese dioxide with a polymer gel electrolyte. And many other research efforts are ongoing with other diverse materials. One thing that seems to be sure though is that as soon as it's possible to mass produce suitable nanotechnology, we will be seeing it in our batteries in some form, and quite possibly in conjunction with silicon. Lithium-sulfur batteries are one emerging technology that can offer greatly improved energy densities compared to lithium-ion. The theoretical maximum specific energy of this chemistry is 2,567 watt-hours per kilogram, compared to lithium-ion's 350 watt-hours per kilogram maximum. This is a huge improvement. A lithium-sulfur battery could be up to 7.5 times lighter than its current equivalent. Right now, lithium-sulfur batteries are nowhere near their theoretical limit, but the ALISE, a pan-European collaboration, are working towards attaining a stable automotive battery of 500 watt-hours per kilogram based on this technology. In terms of economics, sulfur is much cheaper than the cobalt and manganese it would replace, and can be extracted as a byproduct of fossil fuel refinement or mined from abundant natural deposits. Existing lithium-ion batteries are made up of an anode and a cathode between which a liquid electrolyte allows dissolved lithium ions to travel. Lithium-sulfur batteries are constructed similarly, except that the active element in the cathode is sulfur, while the anode remains lithium-based. Researchers are facing a few challenges in bringing this technology to market. Firstly, sulfur is a poor conductor of electricity. Typically, the sulfur atoms are embedded within the matrix of carbon atoms in graphite, an excellent electrical conductor. This arrangement is vulnerable to a process known as shuttling, which causes batteries to drain when not in use, while also corroding metallic lithium anodes, reducing capacity as the battery is cycled. Next, and most significantly, the electrodes physically swell up as the lithium ions bond to them. This is more dramatic with lithium-sulfur than existing chemistries, the sulfur cathode expanding and contracting by as much as 78% as the battery cycles, or 8 times more than cathodes typically used in lithium-ion batteries. As might be expected from this kind of repeated strain, polymer or carbon-based supports and binders fragment and can disintegrate as the battery cycles, reducing capacity and performance. One approach to solving this is to bind the cathodes with different polymers and to reduce their thickness so that the absolute change in dimension is not so extreme. Many lithium-based batteries also must deal with dendritic growth, thin fingers of metal which grow away from the surface and can eventually reach across to the cathode, creating a short circuit and rapid discharge. This is the same thermal runaway malfunction which has caused lithium-ion battery fires in the past, so research for coping with this effect can be carried over to lithium-sulfur technology, including exciting uses of graphene and other nanostructures to act as scaffolds for the deposition of lithium. Solid-state electrolytes could also offer solutions to these issues. Lithium-sulfur batteries are not just ivory tower ideas. Airbus Defence and Space flew a 350 watt-hour per kilogram battery made by Scion Energy back in 2014, powering their Zephyr high-altitude pseudo-satellite. Researchers at Monash University in Australia announced in 2020 that they anticipate having a product ready for commercialization in 2 to 4 years which could provide electric cars with a 621-mile range. A common theme in emerging technologies so far has been researchers' desire to develop solid-state electrolytes. These would replace flammable organic liquids with stable, crystalline or glassy state solids or polymer base. It's hoped that using these solid electrolytes would enable the use of metallic lithium electrodes to provide higher output voltages and allow for increased energy density. Additionally, battery safety improves in vehicle crashes and becomes more resistant to overheating and short-circuiting, in part due to physical blocking of the dendritic growth of lithium and other electrode materials which currently plague lithium batteries. Apart from its theoretical promise, we can be confident that we will see solid-state batteries powering us along the road in the near future, because car makers as diverse as Volkswagen, Toyota, BMW, and Hyundai have all been investing in the technology. Volkswagen, for example, put $300 million into QuantumScape, a Stanford University spin-off. QuantumScape has been holding its cards close to its vest as the website offers no information on their product, only a long list of new job openings, implying company expansion and confidence in their product. It's notable that they hold patents on sulfide-based lithium-ion technology and seem to be interested in thin, sintered ceramic films and lithium-impregnated garnet. One of the difficulties in solid-state electrolyte design is dealing with the expansion of electrodes, which is more difficult to manage in solid materials. A solid electrolyte must be sufficiently flexible to permit this, yet also tough enough to resist dendrite penetration. QuantumScape hold a patent for composite electrolytes to allow them to customize and adjust the physical properties of their electrolytes for such conflicting requirements. Panasonic have also been looking into solid-state electrolytes. It's notable that Tesla have been partnered with Panasonic in their existing lithium-ion manufacturing capacity, but it's Toyota who have publicly announced their collaboration with Panasonic to develop next-generation solid-state batteries. Samsung too are working on solid-state batteries, and in May 2020 described their technology based on a silver and carbon anode, claiming this could give a generic electric car a 500-mile range and survive over 1,000 charging cycles. It may just be a matter of time before solid-state electrolytes are in your pocket and in your car. 2 carbon electrodes and a non-toxic electrolyte, what's not to like? Add the ability to extract more power than from conventional lithium-ion and their ability to charge 20 times faster, and these lithium-ion variants could be the future for electric vehicles. PJPI, an offshoot of Japan Power Plus, have developed this technology with the National Kyushu University in Fukuoka and are currently supplying their Cambrian batteries to an electric bicycle company, Marushi Cycle. Currently, these are single carbon electrode batteries, and details of their exact makeup are hard to find, but they are simultaneously working on a fully dual carbon battery with 2 carbon electrodes, eventually to be manufactured from natural, agriculturally grown products. They anticipate achieving a performance similar to graphene-based batteries, although their Cambrian batteries have a lower specific energy and lower energy density than lithium-ion, meaning that their batteries are both heavier and bulkier than their equivalents. They boast higher specific power. For the same massive battery as a lithium-ion based alternative, it's possible to extract the energy much faster, translating into faster vehicle accelerations. In addition to this, unlike lithium-ion, these carbon-based batteries can be discharged fully. The maker claims that this changes the equation for actual usable energy density, boasting a 40% improvement in range over lithium-ion batteries of the same capacity. Moreover, they say that the battery runs cool and does not require the heavy cooling systems of current electric vehicles. Their claim that a proof-of-concept battery degraded only 10% after 8,000 cycles is very promising. They plan to gradually upscale from low-volume applications such as medical devices and satellites towards mass-market aerospace and automotive customers with a battery made from carbonized cotton fibers rather than exotic toxic metals, with fast charging and exceptionally low battery degradation over thousands of charging cycles. Maybe these will provide long-term, sustainable solutions for commercial vehicles in the coming decades. So much diverse research is underway in battery technology that it's almost impossible just to pick 5 selections. Lithium batteries are found in almost any modern battery-powered product: cars, computers, cameras, and phones. Quadcopters and drones have come about because of advances in battery technology as well, and uses for these machines are mostly held back by current battery life limitations. Better batteries are also important for the advancement of stationary storage from renewable energy sources such as solar power. Tesla is also making headway into this sector, with products like the Powerwall home battery and PowerPack commercial energy storage products. Consumers, technology companies, and industry are all clamoring for safer, lighter, more energy-dense solutions. And concern is also mounting worldwide at the environmental impact of this growing demand for batteries. The technologies discussed in this video could have huge implications on different battery-powered transportation options besides just electric cars. Imagine the potential in everything from electric bikes to electric scooters and electric boats to electric airplanes. Consumer electronics also stand to experience vast improvements in battery life in devices such as smartphones, laptops, cameras, and more. The future is electric. We showcase cutting-edge sustainable technology. If you enjoyed this video, please give it a like and subscribe to our channel. You may be interested in watching one of these videos next. Thanks for watching and have a great day.